Hi everyone. In this video, we're going to talk about Bayes' theorem. So, one really important application of conditional probability and the multiplication rule that we saw in the last video is called Bayes' theorem, and it's called Bayes' theorem because it was named after a man named Reverend Sir Thomas Bayes. He was knighted for his work in statistics and probability. And so, before we talk about Bayes' theorem in total, we need to talk about another law or rule that is used in Bayes' theorem, and that's important. And it's called the law of total probability. Okay? And the law of total probability says this: if you let A1 through AK, so those are K events, okay? And those K events are mutually exclusive and exhaustive, then for any other event B, the probability that B happens is equal to this sum. Okay, and so what that means, so first, what are the important parts? You have these K events, A1 through AK, and they have to be mutually exclusive. And when we mean mutually exclusive, we mean that they cannot share any common outcomes in those events. Okay, so they're disjoint or mutually exclusive, which means they don't overlap in a Venn diagram sense. And they need to be exhaustive. And what it means to be exhaustive means that these events, A, need to cover the whole sample space. There can't be anything else out there that we don't know about. Everything has to be sort of enveloped by A1 through AK. It covers everything. So that's what it means to be exhaustive. Then for any other event B, the probability that B happens is this sum. And so it's a sum from 1 to K, which means it's summing over all the A's. Okay, and it's the probability of B given that A times the probability of A. So that's what we see as, that's in that general multiplication rule that we saw at the end of the last video. B given A times the probability of A. Okay, and so now that I'm thinking about it, the last video, those might have been switched around. I'll talk about that in class, or I might have already talked about it in class once you see this video. But anyway, we're going on. So it's the probability of B given A times the probability of A. Okay, and you do this over all of those exhaustive events A1 through AK. Okay, and so that's how we can get at the probability of B. Now, this probably doesn't make sense at all if you're just looking at the sort of formula. But if we look at a picture of what's happening, it's going to make a lot more sense. So suppose that that box there, the rectangle, is the sample space. And I have 4 events, A1 through A4. Okay? They are mutually exclusive, which means they don't overlap at all, and they're exhaustive, which means they cover the whole sample space. Okay? Another way to say that is they form a partition of the sample space. Okay, and so you'll see A1 through A4 are cut up so that they cover the whole sample space, and there's no overlap. I want to find the probability about B, which is that oval kind of thing. But I may not have that. Okay? But what I do probably have, or I may have, is the parts of B that are in each event A. Okay? And so I may not be able to get to the oval exactly, okay, without the other events A. But what I can do is I can find each of those conditional things, each part of the each part of B in each of the A spaces, add them all up, and then I get B unconditioned on A. Okay, so I can't get at the oval altogether, but I can get the parts. Like I can understand that this much of B is in A3, okay, and what that sort of represents conditionally on the whole. The same with A4, A2, and A1. And so then I can add them all together, and then in a sense I get B unconditioned on those A's. Okay, we'll see in an example how this might make sense in an example, how this might make sense in the real world type of thing. Okay, but that's the law of total probability, and then that is part of what Bayes' theorem says. Okay, so here's Bayes' theorem in its formal sense. A1 through AK, again, be a collective of K mutually exclusive and exhaustive events. Okay, great. These prior and posterior probabilities, we don't need to really worry about what they mean. But we have the probability of the A's by themselves. Okay, so those things that make up the sample space, we know what those probabilities are. Okay, then for any other event B, where the probability of B is greater than 0, we get this. Okay, we get what's in the formula down here. So we can get at the probability that A sub j given B, okay, right here, this, the probability of A sub j given B is equal to the probability of A and B. So simple conditional probability here. We're looking for this. Definition of conditional probability gets us this second part. Okay, A sub j and B over probability of B. Great. Now the law of total probability tells us this denominator part. Okay, this is the law of total probability there. That's the bottom. And then the top is the general multiplication rule coming into effect. Okay, A and B is the probability of B given A times the probability of A. Okay, so that's general multiplication rule right there. Okay, and so that gives us Bayes' theorem. And what Bayes' theorem does, and why it's so important, is that it, in a sense, reverses the conditioning. Okay, I start with knowing the probability that B occurs given A, and by the end, I can flip that conditioning back to A given B. That's incredibly powerful in certain circumstances. All right, so that's Bayes' theorem. Let's go through an example. Okay, and this is an example that is very popular, and it is a real life example of where we see Bayes' theorem being used. So, only 1 in 10,000 adults is afflicted with a rare disease for which a diagnostic test has been developed. Okay, this test is such that when an individual has the disease, a positive result will occur 99% of the time, whereas an individual without the disease will test positive 2% of the time. If a randomly selected person tests positive, what's the probability that the person has the disease? Okay, so this example is talking about testing and sort of false positives and true positives, false negatives, so on and so forth. This example is relevant to us now because I'm sure all of us in one way or another have been involved in testing for the coronavirus, so on and so forth. Okay, and so people are always interested in sort of what's the, how powerful is that coronavirus test? Can it really get it right? How often does it get it wrong? What's the false positive and false negative rate? Okay, those are sort of bad things. And so this Bayes' theorem question is about that. So what's the information that we have here? What's the information that we have? So we have only 1 in 10,000 adults is afflicted with a rare disease for which a diagnostic test has been developed. Okay, so the incidence of this disease is 1 in 10,000, which means you have a probability of having the disease is 1 divided by 10,000. And that probability is 0.0001. Okay, so very small. If we let, so now we need our events sort of that we need to get started with. If we let A be that the person, oh, excuse me, the person has the disease, okay, so that's A, we'll call that A1, okay, A1, the person has the disease, A2 is that the person does not have the disease. Okay, again, sorry for my bad handwriting. And then if we let B be that they test positive, those are events that we're interested in, okay? And so what do we have here? What do we have here? Well, one, I noticed that this is off. It is 0.001, okay? So I was wrong there. Can't do division in my head. So the probability that a person has the disease is 0.001, okay? Which means that the probability that the person does not have the disease is 0.999, okay? We get that from the first sentence. Now, the test is such that when an individual has the disease, a positive result will occur 99% of the time, okay? So that is the probability that B happens given that the person has the disease. Okay, B given A1 is 0.99. Okay, so that's pretty good. It's just like real life situation. Hopefully, given that your disease, you're going to test positive. It does that 99% of the time. That's pretty good. Okay, and then we also know that a person without the disease will test positive 2% of the time. Okay, so B given A2 is 2%. All right. Now, what we want to find out is if a randomly selected person tests positive, what's the probability that that person actually has the disease? And so that probability is given that they test positive, so now B is the given part, that they actually have the disease. So I'm looking for A1 given B. Okay, and so I need to write out what that means. The top part is going to be the flip of the conditioning. So I want the probability that B happens given A1 times the probability of A1, general multiplication rule, okay? And then in the bottom, I need to add up everything. I just need the probability of B happening by itself. And so by the law of total probability, that is the probability that B happens given A1 times the probability of A1. So exactly what was on the top. But then I have to say plus the probability that B happens given A2 times the probability of A2. Okay, that's an A2 at the end there. And so what do we have? If we sort of move over here, B given A1 is 0.99, so it's 0.99 at the top, times the probability that A1 happens, which is 0.001, divided by 0.99 times 0.001. Okay, that's again the first part, plus B given A2, which is 0.02, times probability of A2, which is 0.999. Okay, and so when you do that calculation, the number that comes out, let me do that calculation here for just a second, it is 0.047. Okay, 0.047 is the final answer. Now you could just say, okay, great, I used the formula, I went on to do whatever, and I'm fine. Oh, sometimes this quits out on me. The answer is 0.047. Okay. And so what does that mean in terms of real life here? Randomly selected, if you test positive, what's the probability that you actually have the disease? And so the answer is 4.7%. And I would think usually when I look at this, it seems counterintuitive. Okay? So if you have the disease, you're going to test positive 99% of the time. Okay? And you only test positive when you're negative 2% of the time. So how can, if you test positive, what's the probability that you actually have the disease? It's only 4.7%, which is really low. And the reason for that is that there's just not that many people. Only 1 in 10,000 are afflicted by that disease. So if you go out and test the population, there's not that many diseases out there. And so even though you're only going to get that positive test without the disease 2% of the time, this disease prevalence is so small that if you go out test positive every time, what's the probability that you actually have the disease? It's only about 5%. And so this is what people sort of don't understand about these diagnostic tests, that if you go out and you get a positive test result and you try to look at the numbers in the example, you might get kind of scared that you could have the disease. But maybe this number here will make you feel a little bit better. Okay, so hopefully that made some sense. Now we're going to go on to a your turn. And this your turn is going to look a little bit different than that last example. It might be a little bit more challenging, okay, but I want to use these your turns to give you a little bit of a challenge. Okay? So electronics dealer sells Blu-rays made by 3 manufacturers, which look closely like Sony, Samsung, and PG, but they aren't. Okay, I go through and I give you the lots of probabilities that you need, and then I ask you 2 questions. What's the probability that the next Blu-ray player is defective? Okay, we have some Blu-ray players, some are defective. I want to find out probabilities about them. So just the probability that the next Blu-ray player that's sold is defective. That's 1. And then 2, a customer returns back to the store with a defective player. What's the probability that that was manufactured by NG? Okay, so it's a law of total probability question and a Bayes rule or Bayes theorem question. And I give you a few hints at the bottom to help you along. That's the end of this video.